Today we're going to take a look at section 2.1, which is describing sets. And to start with, let's kind of just do a little bit of vocabulary. All a set is a collection of objects. Okay? So it's very much what you mean when you say, this is my set of history books. It's just a collection of them. Okay? But it doesn't have to be objects literally either. It can be a collection of anything. So I can talk about the set of people in my family. So the collection of people who are in my family as a set. Okay, that would work as well. I can talk about a set or a collection of numbers. Okay, so it doesn't actually have to be physical objects, but it could be. The elements are the individual things in a set. So if I talked about the set as being the people in my family, then my daughter, who joined us last time, she would be an element of that set. All right? There's a couple different ways to describe sets. One of them is the listing or the roster method. So if we're using that method, we actually physically write down everything in that set. Okay? So if you, for instance, wanted to do the description of the people in my family, you would actually list Steph, Krista, my husband and me, Eli, and Abby. We actually put all four of our names in there. The thing you would also do is you put them inside of curly braces. So it would look something like this. So it's still inside of curly braces. There's another method called set builder method. And the set builder method actually, we'll do one of those on the next example. But it has a specific form. So let me just kind of show you what the specific form, generally speaking, looks like. It starts with curly brace as well. It has a letter. And most of the time people like to use X when they're using variables for whatever reason. And then there's a vertical bar, or sometimes that vertical bar will have two dots, like a colon. No, it's not a colon. And this is read all X such that. That bar is read as the word such that. And then usually there's some kind of a description here after this, and then it ends in another curly brace. All X such that these features or these characteristics are true about it. There are some common notations that are used when we describe, in particular, numbers that might be in this sort of a set builder idea. So these common notations are ones that I want to present to you. And some of them you probably have seen before, and some of them you may not have. So the first one that you may not have seen, at least in this context, is the symbol that looks like this. This symbol means is an element of. So that's this idea of here of elements. Is an element of. When we piece it all together, it'll make sense why I've got all these symbols, but for the moment. You might see this symbol or have seen this symbol before. It looks like an N with a double line on the left. If you see it actually written in a book, sometimes it doesn't look like a double line, it just looks like a really bold line on the left instead of a double line. That symbol is for the natural numbers. So you know what the natural numbers are? Yeah. So what we're going to do is we're going to imagine that you're a 5-year-old. Okay, let's start with 5-year-olds because that'll work. You're a 5-year-old. The first time you're starting to learn to count, or what you know to count, the first number you start with when you count is the number 1. 1, 2, 3, 4, 5. So when my son counts, that's how he counts. Those are the natural, or sometimes called the counting numbers. Okay? And then somewhere someone along the way starts asking questions that do something like this. I have 4 cookies and I eat all 4 cookies. How many cookies are left? And the answer is 0, which was not one of those numbers that we just listed, right? So we sort of have to expand our universe to have this idea that there's more numbers than just the 1, 2, 3, 4 that we marked. And when we expand that idea, we come up with numbers that are called the whole numbers. The whole numbers, again, looks like a W with 2 lines on the left. They include all the 1, 2, 3, 4, 5 that we already knew, but they also include the number 0. Okay? So the natural numbers would be the 1, 2, 3. These include 0. And then you have some bright kid in your class that says something to you like, well, what if I do 3 minus 7? about subtraction, right? And as a teacher, you're very careful to do the subtraction since the number that's bigger is always on top. Until some kid says to you, what happens if I try to do 3 minus 7? And as a teacher, you better not say that's not possible, because it is. It's just not what you're learning right now, right? It is. But you need something else. You don't need numbers that look like these. This won't work. What else? What do you need? You need negatives, specifically negative whole numbers, right? You need -2 and -3 and -4, those kinds of numbers. And those kinds of numbers, included with all the ones we had before, make up what are called the integers. The integers is z. So the integers include -3, -2, -1, 0, 1, 2, 3. All the same numbers that we've built up to so far. They just include more. We're sort of building upon our idea of what makes up a number. And we have negatives. So we have the integers. And these actually, it's because of Latin. The word that's Latin for the word integers has a z. That's where that's coming from. Okay, so then apparently somewhere in about 3rd grade, maybe 2nd, just when she brought it home, somebody says to you something like this. I have a whole pie, and my dog ate half of it before I brought it here. How much of the pie is left? And the answer then is 1/2, but 1/2 is not on this list of numbers yet, right? We have to once again broaden our idea of what makes up a number. And we can no longer do this sort of counting trick either. I can't count out for you all of what we call fractions between 0 and 1. It's not possible to do that anymore. But we have broadened our idea to another kind of number. That kind of number, again, is used as a symbol Q. And these are the rational numbers. And just generally speaking, you can think to yourself, these are fractions. And it includes all the ones from before, because I can write any of those numbers I already listed for you before as a fraction. How would I write 7 as a fraction? Close. 7/1. So all the numbers we've listed before, they are rational numbers. Okay? Why do you think we might be using Q? It's not Greek this time, or Latin. That from my class. I'm talking about there? Q, yeah, we did. I remember talking about it now too. So Q is for quotient. Okay? Quotient means what? Do you know what quotient means? Division. And what is a rational number? A fraction that you see the division in it, right? So that's where the Q is coming from. Q is for quotient, and it's coming from the idea of division. Ratio, rational numbers is all about division. Yeah. All right, so then that's all well and good. And then somewhere in high school, you have to do it one more time where you say there are numbers that you can't write as ratios. In fact, you probably encountered one of them before that. You encountered the number pi when you're pretty young, still in elementary school. Pi is not a rational number. It cannot be written as a ratio. Now, there are representations that we use as approximations for it, like 22/7 or 3.14. Those are approximations to pi, but they're not exactly pi. Okay? So when we're taking a look at those kinds of numbers, we need to, again, expand our universe. And we have now R, and R is for real numbers. So real numbers include all of the above, plus things like pi is 1. What else have I not included so far? Decimals are fractions, right? I mean, they just are written in a different way. Irrational numbers, do you have an example besides pi? Square root of 2, that'll work. So not all square roots would work, but square root of 2 would. Square root of, say, 9 wouldn't. Why? Not cubed. It's a perfect square. And what is the square root of 9? It's 3. So 3 is not irrational. It's still real though. All right. It's just more specifically, further up on this introductory list of numbers we've already created. So we're not going to talk too much about which kind of number is what. But we need this in order to be able to make sense of some of the things we're going to be looking at later. Yes? I is an imaginary number, and imaginary doesn't mean it doesn't exist. Okay? Imaginary is a type of number. It's outside of the real number system, and it's used in what are called complex numbers. So the numbers, you don't usually get into I until you get into high school. I mean, I don't know of any that you guys would run into that, but it's outside of this number system. So again, what happens is we get something that we need bigger, because I actually comes from taking square roots of negative numbers. Okay, so it's very much the same kind of thing when the smart aleck kid says to you, what's 3 minus 7? Some kid says to you, well, what's the square root of negative 3? And you have to say, well, that's outside of the real numbers. It's not that it doesn't exist, because there are teachers who would tell you that too, and that's not true. It's just a different number system than what we're working with. It's outside of this idea. Through the question. All right, so we're going to take a look at this kind of description. So this description now in example 1 is actually written out in words. It says we want to write the set of natural numbers, which we talked about just a second ago, that are less than 5. Number 1 we're going to be using is the listing or roster method. So in order to use this method, we start with a curly brace, and we physically write them all out. Okay? So what number will I start with? 1. Then what will I have? 2. Curly brace, we end it, yes. We don't get to include 5 because it said less than. Okay, specifically said less than, so don't include it. So this is the listing method. And this is a great method, right? If I only have the numbers 1 through 4, this is definitely the one that I like the best. But if it said it wanted me to do the listing of all natural numbers less than 100, I wouldn't be keen on that idea. I don't want to list out all the numbers that are less than 100. So there's definitely number system or numbers or sets that I can describe that this works well for, and there are definitely sets for which it doesn't work so well. So let's take a look at the other way of writing this same idea with set builder notation. So again, it's a curly brace, an X, and a bar. It's always going to start out that way. Okay? Then you're going to describe 2 things after that about these numbers. One item it says is that it's natural. It's a natural number. So I've got to do a description for natural numbers. So what do natural numbers have as their symbol? There's an N. Okay? So somehow I have to write down or identify that the kind of numbers I'm talking about are natural numbers. The way that we do that is this. We're going to write an X, just the same as the X from before. We're going to write that element symbol, and then we're going to write an N. So what you want to think about like this. So who has phones and uses texting? Most of you do, correct? You don't text? You never text, okay. This is more flighty then. So pretend you do. You have phones and you use texting, and I will guarantee that some of you, if you texted me the way you text your friends, I wouldn't know what you were saying. Because you guys use shorthand for things that I wouldn't know. I did not grow up with texting. I've only been texting for about 3 years. Before that, I refused. Okay? Didn't want to pay for it, basically. All right, so, yes, you've got a shorthand method for texting. And at one point, the reason for doing so was because the phones weren't so helpful to do this with, right? I mean, like with the iPhone, it's not a big deal, which is why I haven't learned much texting, because that's the only phone that I've ever used for texting is an iPhone. All right? But there was a reason that these shorthand things were done. Part of it was because there was cost associated with sending the data, right? And then there was also this issue of wanting to have it as few keystrokes as possible. In essence, that's what we're doing here. This is the shorthand method for writing things with mathematics. All right? It's the symbols. It's the stuff that allows us to write it out without so much words. That's what we're doing. So this actually says X is an element of the natural numbers. It just means it's a description of what kind of number we're talking about. So this tells me I don't include 1/2. It tells me I don't include -8. It tells me I don't include 0. Are you with me? Awesome. But that isn't all that I was told about this number. It also has to tell you that it's less than 5. You know what that looks like, though. You've used that symbol before, right? So we'll put a comma just to separate it, and we'll say X less than 5. and we'll end our curly brace. So there's two distinct features that we use almost all the time on the inside of these. One feature that describes what kind of number, what number system we're in, natural, whole, integer, real, rational, whatever it is. And then the other piece that tells you what kind of number within that we're looking at. In this case, the numbers are less than 5. All good? All right, this is set builder notation. All right, next idea is the idea of things being equal. Equal sets are sets that contain exactly the same elements. For example, if I were to tell you that we're going to create a set of Dr. Ann's family, and we were to create a set of Abigail Hand's family, Abby's my daughter, they'd be the exact same set. Make sense? Okay. Now, if you want to talk biological, if I described Abigail Hand's family and Elias Hand's family, it wouldn't work very well. Because Eli does have biological family members that are not included in our family. Okay? So blended families are really good examples, and you know, mom, stepdad situation, things like that, of things that would be unequal sets. All right? But equal sets mean just they're exactly the same members. That's different than equivalent, which is a little tricky because equivalent sort of means equal, right? And we're differentiating between the two. And the differentiation has to do with the statement between here, which says one-to-one correspondence. All right. So one-to-one correspondence means that you could actually identify that each set has the same number of things. All right? So for example, if I had a set that had A, B, and C in it, it's just a set of 3 letters. And I have a set of the numbers 10, 13, and 18, or whatever. I could create a one-to-one correspondence. All it means is that I identify one element here with one element here. And I can do that something like that. If I can identify one element in the first set with one element in the second set, and I can only do that if I have the same number of elements, right? That's the kicker, the same number here. If I can do that, we say that it has one-to-one correspondence. And if a set has one-to-one correspondence with another set, then the sets are considered equal sets. Okay. So, at the point when we actually physically get our daughter from Ethiopia home, my family, that I'm, you know, my people that I was there, my immediate family, have 5 people. Okay, I'll have myself and my husband, and I'll have 3 children. My sister's family has herself and her husband and 3 children, which would mean we have equivalent sets. But it's not equal, right? Equal means they're exactly the same. They're not exactly the same. They don't include a single person that's the same at all. But they would be equivalent. Okay, so there is a distinction between the language used there. Okay, so let's talk a little bit more about the one-to-one correspondence idea. So I showed you one correspondence between a set of 3 things and a set of 3 things over here, right? And I just drew the line across, and then I crisscrossed it in the middle, and I said it's sort of arbitrary, like, oh, there it worked. And the question is, like, maybe how many different correspondences could I have created, kind of a question. So that's what this question is getting at. How many different one-to-one correspondences are there between 2 sets of 6 elements? Okay, so let me draw you a picture of what this is asking, and we'll do letters on the left. There's 6 items over here, and we'll do just the numbers 1 through 6 on the right. All right, so think with me. If I paired up letter A, how many different numbers could correspond to letter A? 6. A has 6 different numbers it could correspond to. But once I pick which number that A corresponds to, and I move on, I'm going to look at letter B. How many choices then could I correspond the letter B to? 5. Because one of the numbers, I don't know which one, but one of them was already attached to the letter A. So B only has 5 options left. So what happens when I get to letter C? There are 4 numbers left that could be corresponded with letter C. How about letter D? 3, E, 2, and F, 1. 1. So what you're seeing happen here is you're seeing how many ways different things could happen. And this actually relates to something you may have seen in contemporary math. And this is called a factorial. I can't remember if I actually define it later or not. If I do, we'll define it then. If not later, that's fine. But what we do is we multiply these together. This is called the fundamental principle of counting. The number of ways the whole event can happen is the number of ways each individual piece of it can happen. And you can grab your calculator if you'd like. You're going to multiply 6 times 5 times 4 times 3 times 2 times 1. And you'll find the number of different ways that I could have created this correspondence. Anybody do it yet? 720. There are 720 correspondences. It would make that work. So imagine, this is like the idea that if I had, and this isn't a good example because we don't have the same number, but let's say that we had some kind of a social event, okay? And there were 6 ladies that came and there were 6 gentlemen that came. How many different pairs of people could match up? 720 different possibilities. Is it any wonder that you ladies have a hard time deciding on who to marry? I mean, right? Look how many combinations we've got here. It's craziness. Right? Lots of combinations, lots of ways that something could happen. All right, so 720, just with 6. And there are more than 6 ladies in this classroom. And there are more than 6 ladies on OU's campus. Lots of options. All right, cardinal number. Cardinal number for a set S, the cardinal number, the way that it's written, the notation for it, is an N with the set S in parentheses. And the way that you kind of read this is it's the number of things in set S. So when I put an N on the outside of a set, I'm talking about the number of items in the set. And that's all cardinal number means. It just means the number of items. Okay? Finite sets are sets for which you can actually tell me how many there are. So I've given you some examples of finite sets. I talked about my family, right? My family, cardinal number right now, 4, legally. Right? As in 5 books. 5, if you count what we sort of feel like is our family. We just don't have one of them home yet, right? 5. Now, infinite sets are sets that you can't tell me how many are in. And we've talked about some of those too. In fact, every set that I've described back on the 3rd slide where we talked about natural numbers and whole numbers and integers, all those sets were infinite. And you could look at them because I had to do the dot, dot, dot. You couldn't write them all out. Make sense? Okay. So this is kind of like when there's a passage in the Bible that talks about God talking to Abraham. And he says how many descendants he's going to have and why Abraham has no children. Is that here to sleep too? You guys hear it? No. So God says to Abraham that you're going to have a bunch of kids, right? And Abraham's like, really, I don't have any kids, I'm old. And he says, go out and do what? Do you guys remember what he tells him to do? He tells him to count something. He counts the stars in the sky, and he tells him to count one other thing too. The grains of sand on the seashore. And if he could do that, physically, if he could count them all, that's how many his descendants would be. And he very quickly says, I can't count that, that's infinite. Okay? It's not able to be counted, and that's what infinite is talking about. Now, we do also have a set that's interesting called the Null Set. So the Null Set is a set that has nothing in it. It has a cardinal number of 0. It's denoted as the 0 with a slash through it. And occasionally I'll have students who will come up from high school, and they don't usually come into this class and do this, but I've had it a lot of times in college algebra where I'll have 2 or 3 students each semester who will write their zeros like this. And it's not good notation because this actually has a meaning. It has 2 meanings, in fact. With what we're talking about here, it means a set with nothing in it. Have you seen this notation used somewhere else too? What does it mean? Do you remember? When you encounter it in a different context, it will often mean no solution. So this symbol is not a good symbol because I want to know, do you think that the answer is 0? Do you think the answer is no solution? Because that's what it means usually when I'm teaching is one of those 2 things. In our context, it means empty set. So let me give you an example, and this is only true for probably a limited amount more time. I can tell you about how wonderful the teenagers are that live in my house. They are amazing. They pick up their laundry and they do the chores and they vacuum and they toilet. They're fabulous. And I can tell you all day about how wonderful they are, and logistically, like logically, it makes sense, but only because I have any teenagers in my house, right? I mean, we can talk about things that don't exist like that all the time. And you guys have probably done this in some sense before when you said something like, well, when I have kids, fill in the blank, right? And most of the time, whoever you're talking to looks at you and says, well, we'll just wait and see when you have kids. Or, shut up, you don't have kids, you know what you're talking about. That's the kind of reactions you usually get. Because you're talking about something that doesn't yet exist, right? You're talking about a null set. You're talking about a set of things that don't exist. So we do this, we don't call it that, but we do this and use that sort of an idea quite frequently. All right, so we're going to find, we'll do one more slide, then we'll stop. This one right here, example 3. This one says, find the cardinal number of each of the following sets. What did cardinal number again mean? The number of things in the set, okay? So we're looking at this first one. We've got the numbers from 9 to 99. How many numbers are in that set? How many? 90. So how do you get 90? I think there's more than 90 numbers there. There are 91 numbers there. That's right. How do we figure that? Well, let me show you the way that I think about it. Let's think about it starting back at the number 1. If something started at the number 1 and went up to 99, how many numbers would there be? 99. Well, how many got removed from that description to make this one? 8. Not 9, actually, did they? So this is actually 91. And you know what? Let's give these guys names so that I can use the symbols so you can get familiar with them. Let's call this set A. And we'll say that the n of A then is 91. Number of items in set A is 91. How about the next one? 2, 4, 6, 8, all the way to 2002. 1001. What happened? How do we get 1001 from this set? Okay, so first issue is you're noticing that they're all evens, right? So again, let's pretend like they were all there. If we started at the number 1 and we went to the number 2002, how many numbers would that be? 2002. But if I do that, I've included a whole bunch of numbers that don't actually live in this description, right? I included all the odds. And if you consider the evens and the odds, the evens are half of them. So the number of items, we'll call this set B. The number of items in set B is actually 1001. Of course, good? All right. Now the next one looks a little bit different. It says x squared such that x is equal to 1357 all the way up to 99. And it looks funny, and it doesn't look like the ones we did before. But it actually is more like it than you realize. They're telling you what the numbers are, right? The numbers are actually 1 squared, 3 squared, 5 squared, all the way up to 99 squared. I mean, those are the elements of the set. So if I asked you what are the elements of the set, this is them. Okay? But they're the same number as the 1 through the 99, or the 1 through 99 anyway, weren't they? They're the same number. There's the same number of items here as there are here. They're different items, but they're the same number of items. So how many items are there from 1 to 99 with this description? There are 50. Why 50? Because really this is just the odd numbers between 1 and 100. Okay, again, starting at 1 and ending at 100, there would be 100 numbers, right? But I don't have all those 100 numbers. I have only the odds between 1 and 100, which is half of them. So if this is set C, then the number of items in set C is actually 50. All right, how about D? D says that I want to consider all of the numbers where the number equals itself plus 1. So let me pick a number, just a random one. 5. So does 5 equal itself plus 1? No. So let me pick another number. 0. Does 0 equal itself plus 1? No. That's true, it's not. Let's not use it then, that's true. It still won't work, but how about that one? Does 1 equal itself plus 1? No. No. What should you be noticing? You can't do this, right? There isn't any numbers, there aren't any numbers that equal themselves plus 1 more. That's not possible. So, what is the number of items in set D? 0. The number of items is 0. This is the empty set. No. No. You could say that set D is 0 with a slash through it. But n in front of it means the number of items in there. So we want to list a number for the number of items. So this is the empty set, and the number of items in the empty set is 0. Yeah. All right.